the post lunch session. So this session we have two sort of very good sort of long talks to come, and then a break, and then we have lightning talks before the poster session and then the poster session. And so our first speaker today is a local, so from University of Cambridge and the Alan Turing Institute, Quentin Berthet. He's going to talk about optimal link prediction with matrix logistic regression.
Thanks, Kaveh. And thanks also to the organizer for having us, all of us here. It's really great to see so many people in Cambridge. So I found this sticker. I hope it's not a precious artifact and I'm not going to break it. But so today I'm going to talk about work with Nicolai Baldin, who's a PhD student and is here in the room. And if you have technical questions, you should direct these questions.
Same with me, by the way.
So we're almost done with the work, and I hope I'm not going to do like Andrea and say the same thing.
The mic is not on. The mic is not on.
My mic is not on. Sorry. Now my mic is on. So yeah, I hope I'm not going to do like Andrea, and next time I talk about this, say that it's soon going to be out. So I'm going to talk about optimal link prediction. So it's related to graphs and network. And we're going to have a generative model that comes from logistic regression and matrices. Okay, so there's been a lot of work on the statistical study of graphs. And in general, the idea is that you observe some graph with n vertices. And there's some assumption that the presence or absence of a link or an edge between vertices I and j is related to some unknown property or sometimes known structured properties of vertices I and j. And you're trying to estimate something based on this idea. So of course, there's lots of motivations for these types of models, and there's been a lot of statistical models based on these ideas. One of them is the stochastic block model. So we've already heard talks about this yesterday. It's an unsupervised problem. You see a random graph with independent edges, and the probability that there's an edge between I and j depends only on the community of I and the community of j. Right? So in the vanilla version, there's two communities, and the idea is to recover these assignments tau of I for all the vertices. Right? The graph is generated by a model in this case. So there's a wide literature. I listed people who are in this room and did work on this here, but of course there's many other people who've worked on this problem. Another one that's also related to a statistical problem on the graph, but has a different flavor, is total variation denoising. So it's a supervised problem here in this case, and the graph is used as the structure. So the graph is not generated by a random model. The graph is used in the assumption there's the idea that you have some signal associated to each vertices, and the signal is smooth on the graph, meaning that if you are connected in the graph, you shouldn't be too far, right? And then you have some observations for each vertex.
Right? You can have any q or just q equal 1?
I think this has been studied for different q's. I mean, if q is equal to 2, this is equivalent to, this is a quadratic form associated with the Lagrangian, so it's also very interesting. But I think total variation is usually used for q is equal to 1. Yeah, that's right. So here, the graph is not generated by this model. It's used as a structure, but it's a supervised problem. So what we wanted to work on was a supervised problem, something where you have side information, but the graph is generated by a model. So this is what we have here. So this is the way at least we describe link prediction. We have covariates xi. So this means for every person in the network, you've observed a vector of size t of information. So if you're in a social network, this might be, the gender of the person, their age, what they're interested in, if they're more likely, to buy or sell a cell phone or something like this. And you have partial observation of the graph, meaning that for some I and j and omega, a subset of size n, so capital N is important. It will be the effective sample size here. You observe whether or not there's an edge between I and j. Right? So the idea is that I and omega describes the people who've met in the real world, or have had the opportunity to connect in the social network, and then you observe if they've been connected or not. And the generative model that we have is that for some symmetric matrix theta star that's unknown and that we want to estimate, there's a logistic model that takes xi, xj, and that transforms through this model. So you have some sort of affinity score, xi transpose sigma star xj. And the probability of being connected is sigmoid, right? So of this form of xi transpose theta star xj. So I'll explain in the next slide a bit more why we have something like this. And we assume that all of these variables are independent, right? And we denote the presence of an edge as yij. Okay, the objective is to estimate theta star. So we call this link prediction because this is often how it's called in the networks literature. But actually our objective is to estimate theta star. And we have a block sparse and low rank assumption. So this means that the true matrix theta has k is symmetric and has k columns and k rows where there are non-zero elements. It has small rank as well, and it's bounded in the 1-1 norm, which is a technical assumption. There's several challenges here. The first one is this is a high dimensional problem. The dimension of the problem is d squared might be much larger than the number of observation, which is capital N. And we have some combinatorial constraints. Okay, so are there any questions about first just the definition of the problem? Okay.
The xi are all observed.
Yeah, the xi are known, deterministic, fixed. They're all observed. I mean, if there's an xi that you observe, but you don't observe ever if there's a connection between, if there's no j such that this particular ij is in omega, then the xi is worthless. So it's fine to assume that you observe all the xi's. Okay, so why do we have this particular generative model? The idea is that, as I said, the probability of the edge depends on an affinity. So I think this is a word that technically exists in English, but is more used in French. It's just something to say that it's not only similarity, but it's something that describes exactly how likely people are to connect. Right? So you can write it in this form with the coefficients of s and t. So this would just describe how important these two coefficients are. But if you write it because theta star is symmetric in this decomposition, instead, then this means that the affinity depends on the xi transpose um, right? So there's a few principal axes along which these variables are projected. So this is the score for I, the score of j, and then this is weighted by lambda n. Okay, so if all of these are non-negative, this is equivalent to having a metric, and it describes how the xi and xj are similar. And then essentially this model is just saying if two vectors are close in this particular metric, then they will be connected with high probability. But more generally, this goes beyond geometric description, and you can have lambda L less than 0, which is possible. So the idea is that in some models, maybe for networks, you will not connect because you're similar, but on some variables you will connect because you're different. Right? Let's say that the gender is not observed in xi or xj, but some other variables are observed which allow to determine the gender. If the genders are very different, then maybe in some network models, this means that I and j are more likely to be connected. And the assumptions that we have, so on low rank and block sparsity, they're motivated by this as well. The low rank just says that there's few important vectors, and the block sparsity says that there's few relevant coefficients of xi, xj. The idea is that with, in a lot of high dimensional model, the motivation is that we've collected a lot of information about each person in the network, but we might not know what's important or not. And making these assumptions allow us to overcome the difficulty associated with having a dimension larger than the sample space. Okay? Any questions about? Okay, so this is a bit related to other things that have been explored already. In particular, something like metric learning. So I think it's been written in similar forms. I don't know if it's been written exactly like this, but the idea is that you can have n objects that you will present to people, and there's the assumption that people in their head have a low-dimensional representation for each object. So these objects can be words or images or actual objects, and you want to know or to learn these low-dimensional representations for each object. And the way you gather information is you just ask people, you just show them two objects and you ask them, are they similar or not? Okay. And the idea is that the probability that the person will say that they're similar is related to how close they are in this representation. So let's say everything has norm 1, then the distance is just, low distance is just saying that the scalar product is high. And then it's reasonable to write this model in this way. So this problem is actually recovered by our model. If we just write that the xi's are the elements of the canonical basis, little n is equal to little d. Then for theta star is equal to VV transpose, where we would like to estimate. Then xi transpose theta star xj, which comes from a model, is equal to Vi transpose Vj. Right? So if we're able to learn theta star based on observations related to these, then we're able to learn VV transpose because we're able to estimate theta star. So this is a special case of our model. If we have a parameter space theta star is semi-definite positive and the rank is equal to R, okay, which is a different, again, parameter space from what we have. This is also related to a problem called graph prediction by Bio and Blickley, which is more in the classification framework. So they have a joint distribution on xi, xj, and whether or not there's an edge. There's a true function, there's a true link function, and the idea is that so they're in a classification setting, they're trying through empirical risk minimization to minimize this objective, right? And to find something like eta as well as possible with some noise conditions on it. Okay. It's also a special case of a generalized linear model, of course. So this matrix logistic regression, it can be written as a scalar product. So this quadratic term here in the middle can be written as a scalar product between theta star and some design matrix xj xi transpose. Right? And if this is written again in vector form, so this is just putting the matrix theta star and unwrapping it into a vector, so the vector theta star. And this is a column. This is a column which does the same thing. So we take the vector form of xj xi transpose. Right. So now we have this design matrix that's of size n, capital N, which is the effective sample size, and of dimension d squared. It has these rows, and we have a parameter vector of dimension d squared. And now our model is just a logistic model with this design matrix, the matrix d omega. And this parameter, right, this high-dimensional parameter. Yeah, so this is something that's already been studied, of course, in the literature, with sparsity assumptions on this vector. Here we have structure assumptions that are more deeply connected to matrices, like block sparsity, which is stronger than sparsity, and low rank. So this is why it's more natural for us to see it in a matrix formulation. The other thing that's similar, the other way that it's similar to something else is trace regression models. So in trace regression models, often for some matrix Aij, you observe this kind of product in matrices plus some Gaussian or sub-Gaussian noise. So it's like linear regression except for matrices. Here, this is a different type of trace regression model. It's a trace logistic regression model. Again, with assumptions on the weird structure of the design matrices, the covariates that we have, and theta star. Okay. So we need to make some assumptions in this model. The first reason why we need to make some assumptions is that the problem is ill-posed for the capital N, the effective sample size, less than d squared, which is what we want to look at. So the first thing that we do, which is very classical in high-dimensional statistics, is to make some structural assumptions. Right? So this is something that we've already done, block sparsity and rank, because these are going to be naturally motivated quantities. The other assumption that we make, which is also classical in logistic regression problems, is that the probabilities are bounded away from 0 and from 1. Right? So we have something like this, which means that all of these scores or affinity are bounded in absolute value by capital N. The idea is that if you have some coefficients in theta star which are of the order, 10 billion or minus 10 billion, then the probabilities associated with these coefficients are going to be very, very close to 0 or 1. And the only thing that you see is something related to these probabilities. And then it's very hard to determine if this very large coefficient is 10 billion or 100 billion, which makes a huge difference when you're trying to estimate theta star, but is not translated into a huge difference in the probabilities of the yi's, right? So because the only thing you see are the yi's, it's important to make this type of assumption. So this is something that's already been observed by a lot of people in a logistic regression model for identifiability. It's satisfied here in particular if we make a L infinity assumption on the design vectors and an L11 assumption on the parameter space, right? Which is the motivation for this constraint that we have. And let me just say that Francis Beck has worked, and I think other people have as well have worked on prediction in logistic regression, and in this particular case, it's possible to overcome this technical assumption. And finally, we need to make some assumptions on the covariates. This is also classical in high-dimensional regression problems. And we're going to do something that's similar to what has been done in sparse linear regression, where there's a restricted isometry assumption which is required for estimation. So this is essentially saying that the design matrix acts nicely on the vectors that we're interested in. Right? It doesn't. If you had no noise, it would be easy to invert the problem on these particular sparse vectors. So the way this is formulated is saying that if we look at B, which is an S block sparse matrix, then multiplying it on the left and on the right by X and taking the Frobenius norm on the coefficients in omega is essentially like just multiplying by n the square of the Frobenius norm of B, right, up to this distorted constant. Why do we write it like this? Well, the idea is that the coefficient ij of this matrix is xi transpose b xj, what we're interested in, and that if we again rewrite it in the d omega, vector form, we'll just see that this is equivalent to an RIP type condition on this matrix d omega divided by square root n, right? So this is saying that d omega divided by square root n is close to an isometry for vector forms of S block sparse matrices, right? So this is slightly more technical and restrictive than just sparse vectors. It's vectors of size d square, such that if you put them back in matrix form, they're not only sparse, but they're block sparse. So Traumillin and Gribonval have studied these types of conditions where you look at an RIP type condition, but with different type of restrictions. And I think this is one of the things that they've looked at. This will be satisfied with high probability under various randomness models, either on the xi's or on the omegas, right? So if you sample uniformly and independently the xi's, or if you sample uniformly omega, so the I and j that you're going to test. Okay, so for this, we start with a likelihood-based approach, which is very natural in this type of, and classical in this type of logistic regression model. The log likelihood is written in this form, so it's a concave function. It's very nice. And again, very classically, we have that the difference that we have between the observed log likelihood and the population version, it depends only on a linear form of theta. So again, this is well known in logistic regression models. And here, what's very nice is that the vector that multiplies this theta is very easy to analyze. Here, this matrix is just a sum of IID sub-Gaussian matrices with where this is the random term, which has expectation 0, is bounded between -1 and 1. So you have a sum of sub-Gaussian matrices, essentially. So this has been, again, sum of independent sub-Gaussian matrices. So this has been studied very well. The difference, so when you look at the population matrix now, the population version of this function, again, this is very classical in a likelihood model. It's different from the value at theta star by a KL between these two models. So again, this allows us to understand the geometry of this function around theta star. Again, this is very classical ideas, looking at the strong convexity of this, or strong concavity of this around theta star goes back to Fisher at least. And the control of the deviation terms is just again saying that these are a sum of IID random variables. Okay. And so we look first at least at two estimators for this. The first one is the maximum likelihood estimator with a constraint, right? So with a constraint on the sparsity, block sparsity and the rank. So in this case, the function to minimize is convex. So minus L is convex, and the constraint set is not. So this is going to make it hard to compute. In general, minimization problems that are not convex are not always hard, but this particular one is. It requires knowledge of K and R as well. And it's possible also to do something slightly better, which is to have a penalized version of the MLE. So again, this is very classical. We had a penalty that depends on theta, which depend on the dimension of the model, right, on the complexity of the model in terms of the rank and the 0, norm of the matrix. Right, so again, these ideas are pretty classical in model selection. And that way, it's not required to know K and R. But now the function P is of course not convex, it's not even continuous. And now this problem is going to be hard to minimize as well. Right? So both of these are intractable. But we can at least study what the statistical properties are going to be. And we find more or less something that looks like the right result, which is that the deviations that we get in Frobenius norm squared are, well, up to some term that depends on the conditioning constant of the order kr divided by n and k log d divided by capital N. So this scales pretty much like we expected to scale in capital N, but it also describes well the statistical complexity in terms of the other parameters here of this model. The first term is more or less the statistical complexity of estimating a k by k symmetric matrix of rank R, those kr coefficients. And the second term is the statistical complexity, more or less, of finding the support of size k among t variables. We have matching lower bounds up to constants for this. And of course, as I said before, the both estimators that we have are not computationally tractable. Right? So the two estimators that we have that achieve this performance cannot be computed in polynomial time. Right? It's equivalent to solving an NP-hard problem. So the natural question, of course, which is something that I've looked at in other problems, is can we get both? Can we get optimal statistical rates and polynomial time estimator? Right, so there's some problems that I've looked at recently also on graphs where we can solve this, where we can get optimal statistical rates and polynomial time estimators. And this is something that's been studied as well a lot in the 2000s, where you change all your combinatorial constraints into L1 or atomic norm relaxations, and you get optimal statistical rates. But in this particular case, it turns out that it's not possible. So the first thing that we do is we look at so what's in some sense classical to do in this literature is to change the penalty into something that's convex. Right? So we remove the information on the rank. We we replace this with a 1-1 norm. So this is an L1 coefficient-wise penalty. So this is the L1 norm on all of the coefficients of the matrix theta. And now written in vector form, this is absolutely equivalent to logistic lasso. And so what's the statistical property here? Well, for lambda again of the right order, this is just again rediscovering something that's already well known, rewriting something that's already well known. We get a rate of k squared divided by n log t. What's going on here is that so first, this is a computationally tractable estimator. It's easy to minimize this, but it has suboptimal statistical performance. So what's going on here is that the L1 norm is invariant to permutation of the coefficients. So it doesn't see that having a block sparse matrix is actually a much richer structure than just having a sparse matrix. Right? So it doesn't make the difference between a matrix theta that has k square non-zero coefficients and a matrix theta that has a k by k sparse block of non-zero coefficients. And so this means that we just get the rate for k square sparse matrices, which is much worse. It's of order k square over n. Okay, so this is the minimax rate that we get. This is what the lasso does. So again, this should be D, not P. And so all rates scale as expected in capital N in the effective sample size and the ambient dimension little d. But for the other parameters, again, there's a big gap here in what's going on. So imagine that you have some fixed constant rank R, right? So imagine this problem is for rank 3 block sparse logistic regression. You have a gap from k to k square that's observed in this problem. And again, this is because you don't, in the convex relaxation, doesn't see that the block sparsity structure is much richer than the sparse structure. And there's no natural convex relaxation for the block sparse structure, right? For the 0-0 norm instead of just the 0 norm. Okay. And so in a lot of sparse models and statistical problems, there's been for a while this observed gap between, in particular in block sparse models, between what we're able to do with estimators that are computationally feasible, that run in polynomial, that can be computed in polynomial time, and the minimax lower bound. And so there's been also now a literature on lower bounds for various statistical problems under computational constraints. Right? So this is something that's, that I've looked at with Philippe here on sparse PCA. Other people have studied for dense submatrix problems in Wigner type matrices, community detection, matrix completion, sparse PCA, tensor PCA. So tensor PCA and sparse PCA. So and I might be forgetting some people here. So often this is based on a contradiction argument, a reduction to conjecture the hardness of plan to click. And other people have also looked at other types of arguments for saying that there's computational lower bounds in statistical problems based on other arguments. I've just listed here those that are based on the planted click problem. So I'm just going to go quickly through what this planted click problem and assumption is by digging out some old slides that I have on this. So what is the planted click problem? First, we look at Erdo-Shreni graphs. So Erdo-Shreni graphs are very simple. They are graphs of size n, where each edge is present or not independently with probability 1/2. So ignoring the diagonal, because in this OSI we do the diagonal, well, this just means that all the coefficients are 0 or 1 with probability 1/2. There's no structure, it's pure 0 1 noise. And so the expectation is just 1/2 everywhere. In the planted click case, you take an Erdo-Shreni graph and you take a subset of size k of the vertices and you arbitrarily all connect them. You plant a click. Right? The click is a subset of completely connected vertices. And so in the adjacency matrix, this is going to be a block. And now, just based on this graph, on the observation of this graph, you're trying to determine if a clique has been planted or not. Right, so the expectation is going to look like this: 1/2 with an expectation 1 that's different in this block. And now you're trying to differentiate these two problems. And of course, the clique doesn't need to be in consecutive vertices, right? So instead, it's more like this. Okay, so it looks like something that we have in our problem because we're trying to get a block sparse submatrix of this type. And why do we care in statistics about this particular problem? I mean, it's related to problems on graphs, in community detection, etc. But what's also interesting is that in this model, if the graph is just Erdo shiny, we know that its clique number is going to be bounded above by 2 log n with high probability. And on the other hand, if we plant a clique of size kappa greater than 2 log n, then whenever kappa is greater than 2 log m, well, we know that we can statistically differentiate these two distributions just based on this statistic. Of course, the problem is that this statistic is NP hard to compute. And so people have been looking for other statistics that are easy to compute. This is a problem that came from probability theory and random algorithms and CS. So they want a polynomial time algorithm for detection, for differentiation between these two hypotheses. And what they found is that if kappa is greater than square root m, something over the square root m, which is much larger than 2 log m, then a spectral method will work. And then other things will work as well. The big hypothesis on this problem, or conjecture, is that detection is impossible in polynomial time if you have a clique of a size m to the power c, where c is a smaller exponent than 1/2. So why do we have this conjecture? Well, first, because a lot of very smart people have tried very different techniques and see that all of their techniques break down at this particular point. Also, people have looked at particular ways to describe computation in terms of information theory, and show that in these particular frameworks there are lower bounds of this type. So this is looking at particular hierarchies of relaxations or query models, statistical algorithms by Feldman and that. And then people have started using this as an hypothesis in computer science to show that other things are hard. And so it's used as a primitive for average case reduction, showing that some problem is hard in average case because it's equivalent to this problem. And this problem is conjectured to be hard. Okay, and so how do we do this in this particular problem? So what we want is we want a matrix theta 0 and a collection of matrices with block support S by S. Such that for a given design, so set of covariates, so here again I'm presenting this informally, so let's assume that the size of the graph is equal to t is equal to L, kappa, k, the sparsity is of this order. We want a matrix theta 0 such that the probabilities associated to sigma of this are all going to be 1/2, right? So we have designed vectors and a parameter matrix such that each connection is independent with probability 1/2 if theta 0 is the true matrix. So this is achieved by taking theta 0, which is equal to zeros everywhere, because sigma is equal to 1/2 at 0. And having a matrix of probabilities pi of s, which is equal to 1/2 everywhere, except on a block supported by S, where it's going to be equal to Q, which is between 1/2 and 1. Right? So this is a problem that's even slightly harder than the planted clique problem, because the probability of connection inside the planted set is Q, which is greater than 1/2 but not equal to 1. And so if we want bias of this form, one thing that we can do is we can take xi to be a rescaled version of the vectors in the canonical basis. The idea is that the design matrix in vector form that we get is going to be exactly an isometry here, so we're more or less in a diagonal case. And for a positive alpha such that Q is equal to this, we just take this matrix to be alpha over square root of capital N, so alpha over little n if I and j are both in the set S, and 0 otherwise. What we've achieved here is that we have a collection of matrices theta S, which are at the Frobenius square distance of alpha k square over n from the 0 matrix. And so what happens because of this difference is that if we're able to estimate with an estimator that is computable in polynomial time and for which we have something like this with, let's say, a small constant here. So if we were able to have an estimator that achieves something like this, then what we could do is we could just run this estimator by telling him, yes, that's the problem we're actually making you work on, but instead feeding him or it planted click instances. Right? So we know the matrix X that we need here is just the canonical basis of covariates, and we feed it an adjacency matrix, and then finding if theta star is equal to zeros, in which case we're in the Erdo-Shiny case, or finding if it's some theta S of this form, is going to be equivalent to solve the planted click problem. Right? And so if we could do something like this, then we would have a contradiction on the planted click problem. And this was the rate that we're trying to beat that we're getting with the lasso. Right? So this is just saying the lasso ignores the block structure, only looks at the sparsity, gets this suboptimal rate, but that's actually just a curse of computation. If you want to get something that you can actually compute, this is the statistical cost that you're going to have. Okay, so I think to conclude, so what we have here is a logistic regression model for graphs with non-IID edges. So the edges are independent, but because they are not all identically distributed, we can represent situations where if we're in a metric setting, let's say, we have one vertex that's going to be close to a lot of others, and so this vertex is going to have a lot of degrees, very large degree, a lot of connections, and the other ones can be very sparse. So this is sometimes a criticism that exists for Erdo-Shiny graphs. Here we still have independent edges, but because of this non-identical distribution, we're able to model more interesting graphs, in particular taking into account some geometry that we're trying to learn. We get optimal statistical rates for combinatorial estimators that we cannot actually compute. Suboptimal performance for lasso type estimator, which is a convex relaxation, and computational lower bounds in a supervised regression problem, which I think, at least for planted click, didn't exist already, that shows that the lasso type estimator does the best. I have some open questions about this, things that I'm interested in. The first one is a more general reduction scheme. So we did one for one covariate design. I'd like to see if it's possible to do it for any sort of covariate design. And the other one that I'm even more interested in is more general link function. So modification of a logistic regression model where I think there can be some interesting non-convex optimization problems associated to it that can still be solved reasonably well. And so I should thank our friend on this wall and Alan Turing in London for the support for this work. Thank you very much.
Any questions for Quentin?
So what is the convex hull of the key non-convex thing that you have, which is the set of matrices which are block sparse and which are low rank?
It's not easy to describe, I think, is the problem.
But is it?
So I think I think what's going to happen is you have the intersection between two sets, and it's easy to get the convex hull of each of them individually. And so I think from this you can describe in a little bit implicit manner the convex hull of these two things.
Also, for just the block sparse, you don't have a separation oracle because
I mean, it's a cut polytope.
Otherwise, you could
No,
maximize
yeah.
the.
I mean, it's not easy to describe, yes, because otherwise it would be easy to solve optimization problems on it. you can write it. You know, I mean, I think you can write something a little bit nicer than
what does
just.
it mean to describe, right?
Yeah, you can write something a little bit nicer than just in the convex hull.
Described it pretty well in your question.
But you can't do something like, you know, it's this set of equations or.
Describe means you have a separation.
Well, I mean,
But
it's one way to describe description, but.
so I guess one thing that struck me was that why, so in some sense the low rank kind of disappeared in the computation lower bound. So
Yeah.
is it like subsumed within the?
So no, it's just that. So you can't do both, and in particular, if you start ignoring in some sense R by, let's say, fixing it equal to 2, then these are problems where you can show that there's big gaps between what you can achieve and whatnot. If you ignore K, I think you could do something different, where if you just look at estimators which just look at the rank and try to do something like this, you could get other results, but then you would get an exponent in D instead of K in the upper bounds, and I think this would be even worse in some sense. So yeah, I think here I focus mainly on K by some sense fixing R equal to something. R is less than K already because it's the rank of a K by K matrix. But yeah, I think there would be other ways to describe these types of separations, but this is not something we've looked at. But yeah, it could be interesting.
Any other questions? Okay, let's thank Quentin.